So we start out with the definition of a metric space. All right, so we start with a set. So X is a set. So, and elements of X we call points. So just a quick example. If X is the set 1, 2, 3, 1 is a point on X or of X, doesn't matter. So that's about all I'm going to say about sets. I don't want to go in too deeply. So in order to have a metric space, you need a set and one other thing, and that's of course a metric. So we have a metric. This is a function that takes as its input an ordered pair of elements from X, and it sends it to the real numbers. In particular, it sends it to the positive real numbers, so 0 to infinity, but because of our open bracket, it does not include infinity. So that's kind of a thing, or maybe it does. We'll examine that when we get there, but now just not going to worry about it. So the most important thing is that they're positive. So it can include 0 and positive real numbers. So the second thing that we need for a metric is that if we have 2 points, this is 0 if and only if X is equal to Y. And this is for all X and Y in our set. And 3, we must have symmetry. So we need that the distance d, sort of a distance between X and Y, is the same as the distance between Y and X for every X and Y in X. And for something that is generally the most difficult to check is whether or not the following relation holds, which is called the triangle inequality. So if we pick any third point, the distance between the 2 points in our first part here must be less than the distance between each point and that third point. So it's written like this, and this is called the triangle inequality. And it's important inequality. Right. So in mathematics, whenever we discuss a space, one of the first things that we like to do is define what's considered to be a subspace. So basically, if we have a metric space and the sets are the same, and we have a similar metric that is a metric, then we have a subspace. So let's try to write that out precisely. So if I have y and d tilde, and x and d, so I have two sets, y and x, and two metrics, d tilde and d, and both of these are metric spaces. YD is a subspace of XD if Y is a subset of X, and D tilde is the same as D when restricted to Y. So that's about it. And if this holds true, then we have a subspace. So now we talk about some examples. So the obvious example that we should be familiar with, I suppose, is the real numbers and the metric defined by, so I'm just going to say real numbers and D, where D, x, y, is equal to the absolute value of x minus y. That one's pretty straightforward. The next one is from, well, I'll just call that one. I'm going to call this D2, where we have our Euclidean plane, and the distance between 2 points is the square root of x1 minus y1 squared plus x2 minus y2 squared, where our point is defined as a ordered pair. And that's the same for each, right? So we can show that that is a metric. So now that we have two basic examples, we show something that is not a metric. So for example, if we have our real numbers and a metric defined like this, minus y squared. So we can just check our points. You know, this x minus y is equal to 0 if and only if x is equal to y. That's true. So that's okay. We have that x minus y squared is greater than or equal to 0 for all xy, so that's good. And dxy is equal to dyx. So clearly it's got to fail with regard to the triangle inequality. And we can just show that with the example if we take the point 0 and a half and another point 1/2, 1. So distance, let's see if I'm doing this right. All right, distance between 0 and 1 is equal to 1. The distance between 0 and a half from our metric is 1/2 squared, and the distance between 1/2 and 1 is also 1/2 squared. But we see that D01 is not less than or equal to 1/4 plus 1/4, right? 1 is not less than 1/2, right? So this here is not a metric space. Okay, so now we have some fairly rudimentary examples of a metric space. And now I'm going to discuss a bit more complicated example of a set. So I'm just going to talk about the sets first and then include a metric for them. And I'm not going to prove the metric. So one important set is called L infinity. And this is the set of bounded sequences. So I guess it's more precisely a set of bounded countable sequences. But for an example, if A is an element of L infinity, we can write A as an ordered pair of where a tuple, just some sequence, right? As long as it's bounded. Whatever, it goes on infinitely. So we can write it as a function that takes a natural number and sends it to the complex numbers. And we can write an element like this. This is equal to an, which is equal to whatever, and then an, whatever that value is, where that is the nth position. So we have something like that. And in order to have boundedness, we must have that an is less than or equal to k for all for any index, and there's a k in the real numbers such that this is true. If we have this quality, I guess, this property, then we have boundedness. And a sequence, just a sequence of values. Right? We can define a metric on this, and we can define it like this. you know, where x is x1, x2, and so on, and y is y1, y2, and so on, right? So we can test that out and show that this is a metric. Yeah. And another important set that we'll come across fairly frequently is the set of continuous functions on a closed interval. So we write it like this. So C and some closed interval, you know, this is the set of continuous functions on, you know, on our closed interval, which I'm just going to say subset of our real line. And, you know, it doesn't have to be real valued functions. It could be complex valued functions. So we could have, you know, it just takes it from real to the complex numbers. Or, you know, or no, not, or the real to the real numbers. Right. So, yeah, these will become important further along. And if we remember any of our introductory calculus stuff or introductory analysis, we know that this is a compact set, right? And we have the max for any function in this set, the maximum is obtained. So for t in a b, this exists, the maximum t, this exists and is obtained. So we have that value, and we can define a metric on the continuous functions. So here, remember x and y are both functions, and we can define it as the maximum x of t minus y of t. So the point values, right? And these are also vector spaces. You know, I can add, if I have two functions in the continuous functions, I can add them and they will also be continuous. I can multiply them by a scalar, also continuous. The 0 function is also in there. So we have a nice introduction to some vector spaces. And that's about all I want to talk about right now. Yeah, I'm going to move on from there. Next, I'm just going to talk about some other metric spaces and go over a few exercises. And that's it. Okay.